Okay, so OpenAI is back with another generative model. This one uses natural language descriptions to give us photorealistic images. So if I ask it to give me a photo of an avocado chair, it will give me an avocado chair. I'm not going to lie, that image may haunt my dreams. One interesting application OpenAI emphasizes is the ability of the model to generate results that are easy for humans to verify, making sure the model has an accurate or at least human-like view of the world. The model composes a contrast encoder to create an expressive embedding space and a respective decoder for image generation. I was impressed by the context awareness of the model. For example, in their demo, the model was aware that inflatable flamingos belong inside pools. In the vein of DeepMind's plan to solve everything by first solving intelligence, 3 of DeepMind's initial founders had decided to try their hand at solving the stock market. The stock market is heavily saturated by attempts to deploy the smartest possible predictive model. Little has been said about the exact technical approach being used here, but we can expect that the characteristic brand of DeepMind-style highly general reinforcement learning will be used. Well, maybe. Only time will tell. Right now, if you go to the doctor and get an X-ray, that X-ray is going to be analyzed by an expert radiologist. Or that's true today, but will it be true tomorrow? This human expert may soon be removed from most of these evaluations by new technology up for FDA approval, after having been granted a similar, though less strict approval within the EU. The company which developed the technology, Oxipit, has plans to see the device operational in a clinical setting in 2023, though the American College of Radiology and the Radiological Society of North America advise caution. Quote, "To date, there is a lack of comprehensive research-based criteria for ensuring algorithms are generalizable, and a considerable body of published research to suggest that they often perform poorly across heterogeneous patient populations." It's rare to see a game that AI isn't already playing at a superhuman level these days, but there are still a few high-profile examples. For example, Bridge. A French company demonstrated in a 2-day tournament in Paris that the best bridge players are now of the artificial variety. Their AI won 83% of the rounds it played, a definitive victory. Bridge is very technically interesting because it includes a blend of twists relative to a more straightforward game like chess. In Bridge, there is incomplete information, along with the issue of collaboration across teams, deception between teams, and perhaps the most interesting component of all, explainability, as the game depends on collaboration between players. To accomplish this, the developers used a neurosymbolic approach, which employed a blend of symbolic and some symbolic processes. Using AI to generate convincing-looking paintings is nothing new. Having a robot paint a painting as a human does, that's a different matter entirely. Enter Da, a robot named after Ada Lovelace, a computing pioneer, often credited as the first computer programmer. This project was not developed for the reason you might suspect. It was not an attempt to create revolutionary technology per se, but rather an attempt to critique it. Her work is scheduled for a world premiere later this month. Her painting talent is paired with a language model that allows her to answer basic queries about her work. Titled Leaping into the Metaverse, AI Da Robot's Venice exhibition will explore the interface between human experience and AI technology, from Alan Turing to the metaverse, and will draw on Dante's concepts of purgatory and hell to explore the future of humanity in a world where AI technology continues to encroach on everyday human life. The framing of Dante's Inferno in this slide is brilliant, but I hope it is not true. I think we all hope that. The power of machine learning often lies in its generalizability, but this makes gatekeeping what AI is used for very difficult, if not impossible. In a disturbing new example of the destructive power of this technology, researchers from Collaborations Pharmaceuticals, a North Carolina-based drug discovery company, have published results which suggest the same methods used for drug discovery could also be used to create biological weapons. This alludes to a general difficulty within the field. The power of deep learning comes from its ability to generalize across a wide breadth of data, while simultaneously having the capacity to be adapted to particular applications using fine-tuning. This is further assisted by the interoperability of models and the ubiquitous frameworks they are often trained on. The very technology that lends deep nets their power also presents an opportunity for potential abuse. Artificial intelligence has a critical role to play in combating climate change. Making sense of massive amounts of data is one of AI's strong suits, allowing humans to make critical judgments about the most cost-effective ways to protect the planet. One such project is Microsoft's Planetary Computer, which combines data from NOAA, NASA, and the European Space Agency and other groups to model the climate and drive human decision-making. More generally, AI is combining data from groups around the world, making these datasets interoperable. In other words, using international data to solve international problems. In addition, AI has the ability to make the crisis realer, allowing us to generate striking visualizations of the environment we are leaving our children. This capability is exemplified in "This climate does not exist." This technology uses generative models analogous to deepfakes to bring climate catastrophe to our doorstep. Odds are, if you're watching this video, you own a variant of one of these hockey pucks. And you probably talk to it, and you know that it responds in a very weird, bizarre, robotic voice that doesn't sound very human-like. That may soon be about to change. Meta has introduced their new Generative Spoken Language Model. GSLM aims to add expressive moods, including things such as anger, amusement, disgust, etc., into the kinds of generated speech that we're familiar with. The primary innovation here seems to be that the model directly addresses raw audio signals instead of operating at the text layer. Meta accredits their success to this, noting that when people are in a particular mood, they are likely to use a particular vocabulary. Also, not all kinds of verbal communication involve discrete words. If I laugh at something you've said, I haven't used any particular word, but a human would easily be able to interpret that reaction. These generative models are being put to use decoding what makes a conversation feel natural, as Meta extends their work into the domain of human-like chit-chat. All of this, of course, falls in line with Jan LeCun's long-term strategy of relying heavily on self-supervised learning. Analog computing has been making a return to the mainstream, especially here on YouTube, where those videos have been getting quite popular. People are interested in analog computers. Spin glass is a magnetic state in condensed matter physics, characterized by randomness and cooperative behavior. You can think of spin as orientation in 3D space. In instances of ferromagnetism, which is probably what you think of when you think about magnets, these spins all align in the same direction. However, this more disordered state of spin glass presents the opportunity to realize AI algorithms physically. Researchers at Los Alamos National Laboratory have arranged spin glass in a way that allows it to encode a neural network. Spin glass is not new to the modeling game. Modeling dynamic systems using its theoretical models is an active area of research. This is comparable to a supercooled fluid. The molecules want to arrange in a simpler solid, but can't immediately, because the energy and time to find the ordered configuration aren't available. As a proof of concept, the researchers have constructed a Hopfield network where the value of individual neurons is binary. These nanomagnets are used as physical substitutes for individual neurons in this construction. The magnets communicate in an all-to-all fashion, where each neuron is in constant communication with all the others. With the future of Moore's law very much in doubt, these sort of specialized analog architectures are seeing a massive resurgence, and this is definitely one of the cooler ones. Okay, so this is one of the most fascinating bits of neural network research that I've seen recently. It has to do with what networks are actually capable of being arrived at. What networks can we actually backpropagate our way into? Specifically, this research spells out that some neural networks are possible to define, but are impossible to arrive at using the training methods we have for neural networks today. In an interview with Spectrum, the researchers used an analogy where the resulting neural networks are cakes and the training methods are the mixers used to produce the cakes. A recipe is a definition for the cake, and presumably we are the bakers in this analogy. We are saying that there might be a recipe for the cake, but regardless of the mixers you have available, you may not be able to make the desired cake. Moreover, when you try to make the cake with your mixer in the kitchen, you will end up with a completely different cake. They drew an analogy between these limitations and the famous limitations on mathematics discovered by Gödel, which later inspired the work of Alan Turing. Google just published a fascinating new article on their AI blog discussing the issues of reproducibility when it comes to recommender systems. For example, if I train a model using the exact same process on the exact same data, I can receive quite different performance when I start performing inference. I'm going to read a paragraph from the report because I found it so well written and concise. In practice, deep network models are trained in highly parallelized and distributed environments. Non-determinism in training from random initialization, parallelism, distributed training, data shuffling, quantization errors, hardware types, and more, combined with objectives with multiple local optima, contribute to the problem of irreproducibility. Some of these factors, such as initialization, can be controlled, but it is impractical to control others. Optimization trajectories can diverge early in training by following training examples in the order seen, leading to very different models. Several recently published solutions, based on advanced combinations of ensembling, self-ensembling, and distillation, can mitigate the problem, but usually at the cost of accuracy and increased complexity, maintenance, and improvement costs. The article then goes on to discuss the effect of activation functions on this problem. The work finds ReLU to exacerbate the problem of reproducibility. Specifically, it creates a gradient landscape where the dominant factor of reproducibility becomes the order of examples. Because of its non-continuous gradient, functions expressed by a ReLU network will contain sudden jumps in the gradient, which can occur internally in different layers of the deep network, affecting updates of different internal units, and are likely strong contributors to irreproducibility. The article notes that smoother objective functions have a similar objective landscape, but with fewer regions, giving the model fewer opportunities to diverge. The article proposes a solution in the form of SMELU. We need to work on that name, which tries to capture the best of both worlds. Visually, this is a ReLU with a smooth curve where it contacts the x-axis. They have a really great visualization of this trade-off, where we see the danger of too much smoothness, which causes the model to lose data resolution and approach a linear model. Here's a fun headline: DeepMind proves OpenAI wrong. Well, at least when it comes to laws about model scaling. OpenAI's scaling laws for large language models were found to overemphasize the importance of increasing the size of the deep neural network being used in lieu of training the network on additional data. DeepMind has demonstrated through a series of experiments that the trade-off between model size and training data is roughly proportional. The ultimate proof of this is DeepMind's new Chinchilla foundation language model, which outperforms the Gopher model substantially, despite having only 25% the parameters. This development has large implications for the future of massive transformer language models, with the most obvious change being that we do not need to scale our models any further than we already have, at least for the time being. Instead, we can focus on the comparatively more cost-effective process of increasing the size of our datasets. We live in a world of gigantic language and vision models. These models are called foundation models for the obvious reason that we can use them as a foundation to fine-tune and build other models on top of. These are the results of massive amounts of parallel processing being hurdled at a gigantic set of data. In an interview with Spectrum, AI pioneer Andrew Ng predicts a world of unbiggened AI. Specifically, Ng is after a new paradigm of learning, where the onus of performance is shifted more heavily on the quality of the data itself, and not just on the neural architecture being used. Ng emphasizes that just gathering massive amounts of data and averaging across them is often not very cost-effective relative to investing time in finding better data points and developing tools to refine data, and even using synthetic data to target areas of weakness within existing models. In many industries where giant data sets simply don't exist, I think the focus has to shift from big data to good data. Having 50 thoughtfully engineered examples can be sufficient to explain to the neural network what you want it to learn. Of course, this overarching philosophy falls closely in line with Ng's own company, Landing AI, which is actively invested in improving visual inspection for manufacturing.